This is Temperature Control Lab C for the Advanced Process Control Dynamic Optimization course. We're going to go through this exercise to take some of the data we've collected and try to match it to a model that we predicted in the Temperature Control Lab B exercise. So for that one, and I'll show you a link for that, we had heater values that we adjusted up and down. We measured some of the temperatures from our temperature control lab device, and then we tried to get our parameters as close as we could just by manually adjusting those. In this exercise, what we're going to do is go through the same exercise, the same model, but instead of just manually adjusting the parameters, we're going to be adjusting them with an optimization solver, and to optimally determine them to minimize something like a sum of squared error. Okay, so here's a little bit more information on the model, some of the parameters that we're going to start with. Now some of the parameters that we're going to adjust are going to be things like this heater factor, okay, for alpha 1 and alpha 2. Another one that's a little bit uncertain is the heat transfer coefficient as well. So there's another one that we're going to adjust. Others like constants, like the Stefan-Boltzmann constant, we're just going to, that one's going to be fairly fixed. Okay, maybe the emissivity, we could adjust that too. Won't do that in this one. There's some that we can measure, such as the initial temperature or the ambient temperature. Those are ones that we can easily measure, but others that are a little bit uncertain, and we want to try to estimate those with an optimization solver. Okay, so the temperature control lab has 2 heaters and 2 temperature sensors. Okay, we're going to model this with a couple differential equations. These are energy balance equations, although you can, in our next exercise, we're going to use some empirically derived equations. Okay, and then here are some of the parameters that we're going to adjust. Okay, so just overview of what we're doing. We have this data, and we're going to put our predicted model on top of it and see if we can match those up as best we can. So you don't have to have a temperature control lab device for this, but if you do, then you can generate your own data. I'm going to show you how to start that data collection. So here we go to the dynamic optimization course, and then just scroll down on the side to the Arduino lab, and this just gives more information about the lab and how to get one of the kits. Okay, and then I'm going to go down here to the different labs. We're going to start with ones here on lab B. We'll start with the model here, and what I'll do is just go ahead and select this middle one. Okay, and that's going to give us the code for predicting a model, and we'll combine that with some of our measurements. So just select the get code. Let me show that a little bit. Okay, a little bit better there. Okay, go down to the bottom, select this get code link, and that will give you the code that you need. Okay, and then I'll go ahead and just create a new file. In this case, I'm just going to do a new text document and name this this is going to be TCLab C, and I'll just rename my extension to PY. Okay, but you can create a new Python file however you'd like. Then I'll just create this in Notepad++, just so I can zoom in a little bit on the text and show you what's happening with this. Okay, and so the other thing you can do is go ahead and start collecting some of this step data if you do have a device, and you can do that back here as well. This would be under Temperature Control Lab B or C. I think I included the code for it in both of those. So if you want to start collecting some data, just go ahead and select the get code there, and I'll do that. I'll just go ahead and kick this off. We'll use some data that's also available on the internet though. Okay, so this is this would be collect. You can name this whatever you'd like, and I'll go ahead and just run it with IDLE. Okay, so it's connected to the temperature control lab device, and if you don't have the TCLab there, what you need to do is just come to pip, and you can do pip3 install TCLab, and then it'll go out and get the temperature control lab. Okay, so it collected that and installed it, and then if we run it again and you have the device, then it will start collecting. Alright, so I'm going to go ahead and just minimize this. It's going to go through and start start collecting these temperatures, and then we will see after we're done how well it aligns with our model. Okay, so I'll go ahead and minimize that. And so I'll just go ahead and just add a line here. I'll import pandas as PD, and then let's go ahead and just import our data file, and we'll do read CSV. And if you don't have it, we're going to put a URL here for you instead, so you can just go ahead and read a sample data file. Okay, if you come back here, you can get this from the Temperature Control Lab B. Here's some dynamic data with 2 heaters. And we'll go ahead and copy the link. I'll just right click that and copy the link, and then paste it right here. Okay, so now I'm going to import that data file, and if I just look at it, let's go ahead and look at that data file. I have some headings, just comma separated values. I have time and some heater values, and then the temperatures. Okay, so let's go down to our plot area down at the very bottom, and we'll just add those to our plots. And that's going to be data, and then I'll have time, and I'll need to divide that by 60, and then I'll also have data, and this will be T1. Okay, and I'll make that a black solid line, and then I'll copy this. Now let's go ahead and do this for T2 as well, and I'll make that a black dashed line. Okay, so let's go ahead and just run this one. I'm going to run it with IDLE. I edited it in Notepad so you can see it a little bit better. But if we just run it, this will show us, importing that data file. It'll show us how well we're predicting. Okay, so I'll make this a blue. Okay, so basically the red and the black, they should be aligned, and then the blue and the black here should be aligned as well. Okay, and so what we're going to do is just go through and adjust some of the parameters of our model manually and see if we can get those to align, and that's what the Temperature Control Lab B was. Okay, but if you wanted to come here and maybe double this, the U value, and then or do it here in, okay, I'll just go ahead and double it here, and then I run it again, and then you'll be able to see that you're going to be a little bit closer. So you can guess and check like this, but this is not the best way to do this. You want to use an optimization solver to go ahead and make these two match up. Okay, so what we're going to do now is we're going to go ahead and change some of these to not be just the parameter values, okay, like this, but what we're going to do is go ahead and copy them out, the alpha 1, alpha 2, and the U. We're going to for parameters, those can, special cases of parameters are FVs and MVs. FVs are constant over a time horizon, and MVs can change at any time point, but either you specify those or the solver will specify those. Okay, then we also have, in Gecko we had variables, and those can be state variables or control variables. So those are like special types of variables. So let me just review really quickly what what these are. So if we have a parameter, okay, then if we just want one value of that parameter over the whole horizon, that would be an FV. Okay, and then a manipulated variable is one where it might be adjusted, but we're going to give that value. It's not really determined by a differential equation. It's determined, this one's going to be determined by us or a solver. Okay, and then when we go to variables, okay, variables are going to be determined by differential or algebraic equations. So they're typically going to be smooth. Okay, something like this. And if we have a, I'll go ahead and write MV here. If we have a state variable, looks like my pen is having a little bit of problem today. Okay, or a controlled variable, but it does give a cool dashed line there. I kind of like that. Okay, controlled variable is going to be something where you might have a set point range, and it's going to try to keep it within the set point range. Okay, so that's going to be a CV. Alright, so you have parameters that can become FVs or MVs, and then you can have variables that can become SVs or CVs. Those are like special types of parameters or variables. Okay, and then let's go ahead and just implement this now. So FVs, we can add a couple other things to them if they are FVs. Okay, and one of them is that we can specify upper and lower bounds. So lower bound is, I'll just say that's going to be equal to 2, and upper bound is equal to 30. Maybe I know the parameter value should be within that range. And then let me go ahead and change these to FVs as well. And I'll go ahead and just add lower bound equals, and then 0.001, and then upper bound equals, and let's do 0.02. Okay, so we've added our parameters that we're going to be estimating, and then we have a couple of our variables that we need to try to match up. And one of the ways to do that is just to declare our temperature as as those as CVs, and then try to get those to match, and have basically Gecko handle all the objective functions for us. But let's go ahead and just do this ourselves. I'll do T1 mes, and then I'll just create a new parameter, and the value is going to be from the data file, and these are going to be in Celsius. Okay, so I'll do data T1, and I'll have to do the dot values to get it out of the data frame form, and I'll have a T2 mes as well. So now we're creating our objective function by bringing in the measurement, and then we'll do an objective here, which is going to be T1 minus T1 mes, and then we'll square it. Okay, so there's our very first objective. We can add to it by just adding another line, but now we can have T2 mes minus T2 and square that. Now one of the things we'll have to watch out for here is this right here is in Kelvin, so I just need to convert it to Celsius. Okay, and I'll do minus 273.15. Okay, so now that's Celsius minus the other Celsius, which is measured, and I'll square that. Okay, so this is we've made these modifications right here. We've identified which parameters we want to use. The one final thing that we'll need to do is just turn the status on for these, and that just tells the solver that we can use those, and they become degrees of freedom. So those are going to become 3 degrees of freedom that we're going to use to be able to optimize our model, be able to fit this objective. And this m.obj, it always minimizes the quantities. If you ever want to maximize something, you can just multiply by -1. So if you want to maximize the area, you can just do negative there. Okay, and then the final thing that we need to do, I'm going to scroll down to the bottom, is go ahead and switch this to iMode 5. And that becomes an estimation algorithm mode that it'll run in. So if you just search for iMode on APMonitor, you'll find the different modes of operation that you can run in. So we're going to switch from dynamic simulation to dynamic estimation using a simultaneous approach with our collocation equations. So let's come back here and we have iMode 5. We'll go ahead and solve it, and let's just see how this one does. Okay, so I'm going to just run this with IDLE. Okay, so I had some invalid syntax right here. I just need to do comma to separate those. Okay, so T1 is not defined yet. What I'll need to do is just move, where I define this objective, I need to move it down below where I define T1 and T2. Okay, so now they're defined, and so I can use them. And I'll try to run it one more time. Okay, so you can see had just popped up fast. I'll go scroll back up so we can look at it. Okay, and there is our, this one just finished our, I did this again. I did this on an earlier video too, where I forgot to turn on the heater for this thing. So let me just go ahead and plug that in again, and I'll run it. I don't know why I do that multiple times. I forgot to plug in the heater. It was running, collecting data, but heaters were not plugged in. Okay, so anyway, I'll start that again in just a little bit. Okay, so we have temperature 1, temperature 2. We have the measured values, which are the black line, and then the predicted values, which are here in the the colored lines are the predicted values. And so you can see those match up a lot better than they did before. And let's say we wanted to now print out the values of these right after the solve. We can do that with print, and let's do our u value, and we'll convert to a string, and so we'll do u dot value. I'll just take the first one because it reports it as a vector. Okay, and then we want to see the alpha 1 and alpha 2 as well. Let me just grab these, and I'll do alpha 1, and I'll change this to 2. Okay, and then I'll change this one as well. Alpha 1, and change this one to 2. Okay, so let's go ahead and run it one more time and just see what it gives us in terms of the numerical values. And one of the reasons why we want to check these at the very end is just so we can see if it's going to be constrained. Okay, so it's going to, we are not constrained by our upper and lower bounds, so you can see those values right there. Okay, so this is right here, this is a script that'll do that. We had our data that we imported. If we come down here, we defined our parameters. We changed those from param to FVs and then turned their status on. We brought in the measurements ourselves, and then we formulated an objective. Okay, let me show you how to do this with using the built-in APMonitor objectives, the Gecko objectives. Okay, so instead of bringing these in as, I can have T1 mes, for example, right here. And I'm just going to say that equals data T1 and data T2 dot values, and then I will add 273.15 just to get it back into this will get it back into Kelvin form. Okay, or I could just leave those out, because we might want to plot them later. Okay. And then what I want to do is just go ahead and take my T1 and T2, and I'll move those to CVs instead. Okay, those are going to be controlled variables, and then this is going to be T1 mes plus 273.15, and then this one is going to be T2 mes plus 273.15. Okay, and then I can go ahead and get rid of these, and then I'll have an option. Okay, and then I'll change my EV type, and then I can change it to 1, which is like a sum of squared errors, and I can control things like a okay, and then this is, I have a number of options that I can use with this as well. Okay, so let's just go ahead and search up the documentation for this. This is our estimated variable type. And so you have an option to do 1, which is like a linear error. It's like an absolute value, minimize the sum of the absolute values, or you have the squared error, and then this one does a third one. It's kind of a developmental one. Okay, and then if you look at estimation objective tuning, there are a number of other parameters that you can adjust. Okay, with and I'm going to go here to estimator tuning on the right. Okay, let me show you where that was again. Okay, right here on estimator tuning. And this one, it shows you this Python widget that you can use to give a better intuition about some of the parameters that you're adjusting and why you might be adjusting those for your estimator. So I would recommend that Python widget right there. Okay, so here are a couple other ones that we can use that are typical. For FVs, here are some of the typical tuning parameters that we'd use. Manipulated variables, here are some of them as well. Okay, and then controlled variables for estimation. We can also do this MES gap, so we can try to not fit the noise of our system. And so, I can do m dot. Okay, so I'm going to do t1 dot MES gap. Okay, and so I can set that to be something like, I don't want to fit anything if the fluctuations are just within plus or minus 0.1. Okay, so there I have a different type of objective that I've configured, and it uses the gecko objects to do the objective function. So let's go ahead and fit this one now and see if we get a different result or about the same. Okay, so I had a few more variables there because it puts some additional slack variables and other things around it. Okay, but it gave comparable results. So you may want to use like a EV type 1 if you have outliers and you don't want to have your objective function be heavily influenced by some of the outliers, noise or drift. And so I have some articles that show why that's going to be better in those scenarios. Objective function, if we want to switch back to a squared error, then we wouldn't use these two. To get the exact same results that we got before, we just do EV type 2. Okay, and then if I run that again, I should get similar results. You'll see that the model size will be a little less large there. We'll just have the 3 degrees of freedom that you see right here. Okay, so number of variables after we did all the collocation are going to be 2,400, and then we have the 3 parameters that we're estimating. We have, these are equations, the collocation equations and the energy balance equations. So we had 3 degrees of freedom that we're going to be fitting. You can also look at the objective function right here, and so you want to evaluate how your model is doing and how it's fitting with that objective function. That would be a way to quantify the performance. Okay, and then now the final thing that we can do with this lab is run this estimation as we get new data. So we don't just have to do it once, but we can run it continuously as we go. And that's called moving horizon estimation. And we keep a certain horizon of data and then the last one will fall off. It's kind of like this right here. We keep a horizon. If you add an additional point here to the current time, then the last data point is just going to fall off. We're going to remove that from our horizon. And so there's a way to do this in Gecko. Okay, I'm going to come back here. And if you'd like to run the moving horizon estimation, just come here to grab the code. And let me just highlight a couple things just as this is running. Okay, it's going to do this loop and do this parameter estimation on every cycle. So I'll just go and grab this code and do a final one here. mhe.py, and I'll paste it in, and this one I'll just run, and now my heater's plugged in, and I'm going to try to check that next time when I run this again. I'll just check to make sure that my heaters are in fact plugged in. Okay, so here we go. We have these heaters, okay, and these temperature sensors. Now I'm running in this local mode, so you will see the executable window pop up sometimes. Okay, I don't think it does that on Linux. So anyway, you can see the model and the estimator being adjusted. At 30 seconds, I tell it to go ahead and start adjusting the parameters. Okay, so you can see the first adjustment to the parameters right here. And so it's going to try to align the predicted values, which are in the black lines, to the measured values, which are the dots, the red dots, or for temperature 2, it's going to be these blue X's. Okay, and so as it goes, it's going to adjust those parameters to try to minimize the sum of squared errors between those. Okay, so let me come back to the source code. So I'd encourage you to run this. You can blow on the heater, see if you can get a different heat transfer coefficient, for example. It'll change that. Something you can't measure, but you can infer from the data. Okay, so I'll go ahead and just close this one. Okay, and I would say if you're running on a Mac with this one, you do have to change the remote when you connect to when you do your Gecko model. You'll have to change this remote equals true, because there's not a local executable for Mac OS yet. Probably will in the future, but for Windows, Linux, or ARM processors like Raspberry Pi, there is a local executable. Okay, so here I have MHE, and let me just go and run through this code just a little bit so you can understand what's happening. Okay, here's where we connect to the TCLab, and we're going to specify some of these steps here in the heater values. Okay, and then we'll also have some random changes to those heater values as well every 5 cycles. And so we're cycling every 3 seconds, so I just need to store some values for plotting. I'm going to initialize the estimator model. Okay, so here's my Gecko model, and I'll go back 21 time points. That'll be about a minute in looking backwards, try to estimate these parameters. Okay, here's my U value that I defined previously. I'm not going to estimate that initially. I'll turn the status on after 30 seconds. And then I define some lower and upper bounds. So you can either do LB here and UB, or you can put your upper and lower bounds right here. Here's how much you can move that parameter each cycle. Okay, F status is whether it's feedback status, whether we have a measurement for that parameter or not. So we don't have measurements for these parameters. Okay, I'll do the same thing for alpha 1 and alpha 2. Okay, the rest of this, these are going to be Q1 and Q2. We'll set them up as MVs right here, because later on for predictive control we'll set those up as manipulated variables. And the rest of it, these are going to be our CVs, and there you can see some of the tuning parameters that we discussed previously when we did it just once. Okay, here's our model that we have with our energy balance, with 2 equations that are energy balance. So we reviewed those in Temperature Control Lab B. And then these are just some of the options. Run in MHE mode. There's a squared error objective, number of collocation nodes. We use the IPOP solver. And we'll also cold start on the first cycle to help us better initialize. Okay, we're going to go ahead and create a new plot, and then we'll just put up some things here with timing. Be able to time our loops, make sure we stay at about 3 seconds per loop. Okay, so that's all this timing right here. We'll sleep for a certain amount of time. That just allows us to maintain that certain cadence to measure temperatures every 3 seconds. We'll read the temperatures from the Arduino device. we'll insert the measurement. So this automatically inserts the measurement into that horizon, and then bumps the last one out. So it's going to take care of all of that within Gecko. So all we have to do is just insert the current measurements for the heaters and the temperatures, and then it takes care of formulating the objective and time shifting our model for us. Okay, after 10 cycles, that would be 30 seconds, I'm going to turn the status on for those parameters. Then through every cycle we'll solve. If our application was successful, we'll check the app status. Then we'll grab the model values for our CVs, and then for our parameters we'll grab the new values. But if the solution failed, then we'll just copy the prior solution and hope that we'll get a successful solution on the next cycle. Okay, we have these values, the heater values that we got from, we specified some steps in those. And all of this is just creating that plot. Okay, we're going to draw it, and we'll pause just a little bit just to let the plot catch up. And at the very end, after we go out of that loop, we'll turn off the heaters and then save a figure. Also allow for some keyboard interrupts like Control-C, so we can shut off the heaters if we see a Control-C. Okay, or if there's an error, it'll just shut down and save the plot. Okay, so that's it for moving horizon estimation. I would recommend that you run that, even if you don't feel like you have the experience to program that yourself. I would recommend that you run it, and you can change things, the tuning, other things on that moving horizon estimator. The purpose of this assignment is really get an intuitive understanding about what an estimator does and how it performs, and then later on we're going to be getting more into the mathematics behind it. So I hope you enjoyed this tutorial exercise. I'll go ahead and post this to YouTube, and I hope you feel free to leave any comments in the comment area below.